Okay, well, thank you very much, and thank you to everybody for joining today's webinar on RF and microwave device challenges with 3D components that Modelithics will be delivering. But before we go into that presentation from Modelithics, we thought we'd spend a little bit of time just giving you a quick overview of exactly what these 3D components are and how they fit into HFSS design flow. So 3D components, if you think about how we design, for example, with something like this smartwatch, a smartwatch is assembled through essentially components, three-dimensional components, such as if you take an exploded view of the smartwatch, you'll see that it's made up, of course, of a wristband, but if you explode the watch itself, you have mechanical parts like the bezel, you have circuit boards, you have flex cables, you have shields, you have an arrangement of 3D parts or components that are brought together to make a single device. And those parts or components could be designed in-house, could be manufactured in-house, or more likely, they're probably designed and manufactured outside from a vendor, and as a system integrator, you bring them together to create your device. Well, with ANSYS 3D components, we do the same thing with simulation. We think of these 3D components essentially an equivalent to a circuit component that we use in any one of our circuit simulators. If you think about when you drag and drop one of those boxes into a circuit schematic, that box is really an encapsulated file of, maybe of a SPICE netlist where you're just exposed a few key parameters of the design, such as with an analog to 3D components, these 3D component models contain information associated with the geometry, the materials, any excitations that might be associated with the component, as well as boundary conditions or mesh operations. These components, as would be the case with a component in circuit, can be parametric. You can define what parameters are exposed to the end user, and that control is actually provided to the component creator or the vendor creating the component. And in addition, we have IP protection technology, which can optionally be applied to a component, which gives the vendor or the creator component the ability to provide all the high fidelity information of the 3D model to an end user, but protect their design by not exposing the geometric detail of the design or the fields inside the design or the mesh inside the design. And again, that's an optional feature that you can define for a 3D component. Now, who can build and share these 3D components? Well, anybody who has ANSYS HFSS has this capability, has this technology. There's no additional licenses or products to acquire from ANSYS. And so essentially the way it would work is you have your component created in ANSYS. It's parameterized. There's a command you go to where you say, I'm going to create a 3D component that encapsulated into a particular design file, and you can share that design file with any end user. It could be someone inside your own company, a colleague, or it could be an outside entity like a partner or a customer or a vendor. So component vendors can take advantage of 3D components. An analyst who wants to have a detailed model of a structure that they themselves don't want to go through the trouble to build, or maybe can't go through the trouble to build. Of course, anybody doing system integrators should see value in this component capability because they can get detailed designs from partners and vendors to do a full fidelity 3D simulation with HFSS inside of HFSS. And of course, modeling specialists, such as we'll hear from today from Modelithics. Now, the ANSYS vision is to provide full simulation for a complete product. So today we'll be focusing quite a bit on electromagnetics, but of course we're ANSYS and we want to deliver full multi-physics simulation. So we want to enable people to do a complete system modeling, and these 3D components are really a key part of delivering this vision. With 3D components, we can enable a new approach to design, where we can make simulation more accessible. And by that I mean someone doing 3D simulation doesn't have to be an expert in creating components, geometries, and parts. They can get that information from an outside expert or an internal expert within their own company. So it makes the whole simulation process more accessible. We also enable industry collaboration by a key feature of this encrypted technology with hidden content. This allows people to share their designs but not give away their IP, but know that their designs are being designed into a system with the highest fidelity possible model. And because it's all inside a parameterized and automated interface, you can also enable design optimization and exploration with this technology. So real quick view of the desktop and 3D components. So the way this will exist, and this exists today, we've had 3D components out for 3 or 4 years now. There's a component library tree on that can be exposed on the right-hand side of the window, and then the user will just drag and drop whatever component they might want from this library into their simulation. And they can move these components around, they can do rotations, they can place them into the appropriate place in their system and run a full simulation, no compromise, full HFSS, fully coupled simulation inside of HFSS. So these pre-made models come together to create the whole system. And then an example here, and this is actually an example of an example project that it comes with HFSS today. This is a chip antenna from Johansen on a test board that Johansen provided to us for inclusion in our example project folder. And so in this design, there is a 3D component with encryption technology and hidden content placed onto the test board. We run the simulation. This is a completely typical flow with HFSS. You create solution setups. Everything from that point on, after creating the geometry and bringing in the 3D component, is actually exactly what you're used to today. You can plot far field patterns. You can plot S parameters. And again, I want to emphasize this is a no compromise solution, even with the encryption technology, because HFSS is fully aware of where all the geometry and what all the material properties are. They're just not exposing it to the end user if you're using encryption. And just to give you a better look into that, if you zoom in on the chip antenna model, you can actually see we've done a cut plane view of the field plot through the antenna, and you actually cannot see the fields or the geometry interior to the component. And it is the creator of the component who has this control over whether information is encrypted and hidden or not. They can decide what parts can be exposed to the end user. In this case, the feed points on the antenna are exposed, so the end user knows how to place the antenna, but from there, everything else is hidden. So quick example, let's say I'm a drone designer and I want to integrate a GPS antenna for location. I get a GPS component model from a vendor. I can place it on my drone, and then I can perform the following operations with 3D components. We can verify antenna system performance. So although I may have gotten the performance of the antenna on an ideal ground plane from the antenna designer, I want to understand how it actually operates in my system. I could optimize the antenna location, antenna performance. Maybe there are certain parameters of the antenna that have been given to the end user that they can adjust. You could look at that, or you could even optimize the antenna location by using a parametric antenna placement coordinate system. What an integrator, what an end user doesn't need to do in a flow like this is they don't need to create the antenna geometry. They don't need to be an antenna expert. That can be the vendor or the component creator who does that part of the job. They can have a parameterized antenna. Again, that can be enabled by the creator of the component, the vendor, and they don't have to do the assignment of materials and excitations, because then that's controlled by the subject matter expert, the person who actually knows how to do this part of the design. But what integrators can do is design for tighter margins, because now they have a full fidelity model, a no compromise model, more than just an S parameter block. They're accounting for all the coupling that may or may not occur between the component and the other components in the system or the system itself. And in the end, design with higher confidence of success when you actually go to build the product. For vendors, this could potentially reduce engineering burden for device integration. So you don't have to work maybe as much to help your end user to integrate your device onto their system, because they have this ability to use this full fidelity model, and that can give you a competitive advantage in the market when you're trying to get your device built into a system. And it's not just antennas. You can also see that you can do a connector design mounted on a board. Here's an example where we have a PCI Express connector mounted on a board. And in fact, in this example I'm showing you here, we're using a combination of HFSS 3D layout for the board design and HFSS 3D for the connector design. And finally, to wrap up and move on to the heart of the presentation today with Isabella, HFSS 3D components, it's an integrated drag and drop workflow, easy to use for all designers, very, very simple. You don't have to be an expert in a particular device. It can be provided for you. It enables design collaboration, which can lead to tighter design margins with these higher fidelity 3D components, and of course, protect vendor IP through the encryption and hidden content. So with that, I'll turn it over to Isabella, and she can go into the part of the Modelithics presentation.
Thanks, Matt. All right, well, hi everybody, my name is Isabella Bedford, and today I'm going to discuss what Modelithics is doing to help 3D component modeling, to incorporate 3D component modeling and help RF and microwave design engineers solve their integration challenges. So here's a quick overview of what we're going to cover in today's presentation. First, I'm going to give you a brief introduction to Modelithics and what our offerings are for HFSS. We're then going to examine some equivalent circuit models and what to provide as far as suitable accuracy in simulations. Then we're actually going to cover some test cases where you're going to see that full-wave 3D EM simulation is necessary to design success, and equivalent circuit models and planar EM just won't cut it. The 3D EM simulation setup is actually quite an involved process and requires proper setup to yield accurate results, so we're going to discuss some of the common issues that are encountered when you set up a 3D EM simulation. And finally, we're going to cover what Modelithics and ANSYS are doing to help designers overcome these issues. So a little bit about Modelithics. We were founded in 2001 as a spin-out from USF, and we're currently in our 18th year of business. We sell and support highly accurate model libraries for discrete components, and we also offer custom measurement and modeling services for many different devices. We offer long-term model support and maintenance for several simulation tools, among those HFSS, and we also have many years of experience with HFSS use and other EM simulation tools as well. So Modelithics' premier offering is our complete library. This library contains over 625 active and passive component models representing over 16,000 commercial off-the-shelf components. So I'm just going to go over the libraries that are included as part of Complete. So first of all, we have CLR library, which is our largest library and contains capacitor, inductor, and resistor models. These models are highly scalable versus part value, substrate, and pad size, to name a few features. We then have our NLD library, and this is our diode library containing, once again, substrate scalable, temperature-dependent models for various diode types such as reactors, pins, and Schottky diodes. We also have our transistor model library, the NLT library, containing FETs, BJTs, just to name a few, and these models also have advanced simulation features such as the substrate scaling, temperature, and bias dependence. Our SLC library contains system-level components for devices like filters, switches, and amplifiers. And we also have a library called the SPAR library, and this is a grouping of single substrate measured S-parameter datasets, which are packaged for your convenience. So Modelithics models address the industry need for high-accuracy RF simulation models that represent thousands of commercially available electronic components from many popular vendors. Our models are standardized across various vendors. We offer enhanced scalability features, and using our models provides significant savings versus in-house modeling. So specifically for HFSS, Modelithics has a special version of our complete library called Complete Plus 3D. Sorry, I think I'm hearing that the sound is not clear. Can everybody hear me okay? Guess I'll continue. So specifically for HFSS, we have the Complete Plus 3D library. This library contains our CLR library and additionally all of the available 3D geometry models that we offer. As always, these models, sorry, okay, the sound is okay? Everybody can hear me? As always, our models are measurement validated and thoroughly documented with a model data sheet. ANSYS's unique encryption technology enables us to leverage our relationship with component manufacturers to get physical and material information under NDA. We can then build 3D models and distribute these models to third-party customers, all while protecting manufacturer IP. So, all Modelithics models are developed using consistent precision measurements and extensive validation. Our microwave global models, in particular, simulate parasitic effects, accurate ESR, G-factor, and higher-order resonances as well, helping predict broadband performance. The scalability and de-embedding features of our models allow for flexibility in simulation and enable accurate EM co-simulation as well. Our goal is to help streamline the design process and help designers achieve first-pass design success. So, when are circuit models sufficient for design success? Traditionally, measurement-based equivalent circuit models are the best solution for surface mount passive components as well as discrete or mimic active devices. The advanced pad treatment that's available as part of our models and our passive component models as well as our active component models allows the user to de-embed solder pad effects from the equivalent circuit model itself. So the user can then include their own custom pads as part of an EM co-simulation to get the most accurate results for their test fixture. This is a very popular approach among our customers, and they have reported to us great degrees of success with rather complex designs. These equivalent circuit models are flexible and they can be simulated quickly. However, the issue with equivalent circuit models is they're generally developed in isolation and can't account for component-component coupling or other interactions with components environment. So what I'm going to show here is an example of an equivalent circuit model in a planar EM co-simulation situation where we were able to actually accurately predict the fabricated circuit performance without having to use 3D simulation. So the example here is a 5 gigahertz elliptic high-pass filter. This was originally designed using New Hertz Technologies filter solution software. And this particular filter was built on a 20 mil Rogers 4003C board using a combination of discrete SMD components for the capacitors and distributed elements for the radio stubs to achieve the desired filter response. The measurement data is shown here with the blue line, and the circuit simulation results in red are shown to provide reasonably good prediction of the fabricated circuit performance. However, compare this to the improved results that you can achieve using EM co-simulation, particularly planar EM co-simulation in the situation shown in magenta, and we were able to better capture the out-of-band performance of the filter. In this case, the lumped and distributed components were separated by enough distance for this application that the equivalent circuit models in planar EM simulations gave us excellent results. So, when would a 3D EM simulation actually be needed? So as previously mentioned, the weakness of equivalent circuit models is that they're developed in isolation. So generally, you can't account for any of the component-to-component coupling, component to the surrounding environment coupling. When all of your components in design are spread out and separated by sufficient distance, or the design is relatively low in frequency, this won't affect your results generally. Circuit simulation of components and planar EM simulation of the traces will typically be enough for designers. However, compact topologies, higher design frequencies, and increasing product complexity can mean more electromagnetic interactions between closely spaced microwave components. You can see this here in the illustration shown on this slide. Shown here is a cut plane view of the E field of 3 capacitors that are placed in a shunt configuration on a 50 ohm line. At their closest spacing, the fields surrounding the capacitors are clearly interacting, as you can see. This sort of unexpected coupling in your design can result in performance degradation and lead to costly and lengthened design cycles. Using full-wave 3D EM analysis can mitigate much of this on-the-bench tuning that would be caused by these effects had it not been caught at the design stage. So, full-wave 3D analysis is the key to capturing these sorts of interactions at the design stage and accounting for them prior to fabrication. However, 3D EM setup is not really a trivial matter. To obtain good results, it's critical that the designer sets up the model environment to match the test environment as closely as possible. This includes modeling not only all of the traces and substrate, but also requires the physical and material properties of discrete components to be modeled within the circuit. This is one of the biggest problems designers face, as this sort of information about discrete components is typically proprietary manufacturer intellectual property, and that's not available to designers. But luckily, Modelithics has trusted relationships with a lot of these component manufacturers, and this can be a real value add to designers. Since we've been working with these component manufacturers for years, they allow us to have this sort of information shared with us under NDA. And it's really ANSYS's unique encryption technology that allows us to use this information to build encrypted 3D models, protect manufacturer and our IP, and then distribute them to third-party customers for use in their circuit designs. So another difficulty in 3D modeling is that even if you have all the required information, your initial 3D model results might not be that good when compared to measurement data. This could be caused by a number of reasons, ranging anywhere from manufacturing tolerances to the actual physical dimensions and geometry of the component, or material property uncertainties or incorrect property definitions. And it can even be simulation related, so issues such as port configuration, meshing, etc. So because of this, measurement validation is really crucial along with EM simulation expertise. Modelithics has extensive experience in EM simulation and already has a large database of the measurements needed to perform these sorts of 3D model validations. We also have the ability to obtain additional or new measurements as needed. One of the most useful features of 3D models is that even if they're validated under specific conditions, test fixtures, that sort of thing, the nature of a full-wave EM model results in a much more general model than an equivalent circuit model. So this will enable analyses of complex circuits that account for component-to-component as well as component-to-package interactions. Now, examples of such simulations will be shown in the following slides. So in this test case, we have three 0603 size inductors that were placed in shunt configuration on a 50 ohm line. So component separation was varied from approximately 1 substrate height to approximately 5 substrate heights to study coupling effects. Results from the circuit simulation of this test picture and the components was done and compared against measured data in the plot shown here. So, excuse me. This was done using Modelithics models for the inductors and the simulator's built-in transmission line models. On the right, results are shown for the same configuration, but now using full 3D EM models for all components in the design, for the inductors, traces, vias, everything. So you can see here that the circuit simulation fails to capture the trend of the resonances as the separation between components is varied. And although there is a slight shift in the 3D EM simulation, this could be due to tolerances potentially, the 3D simulation correctly captures this trend. To better illustrate this, we plotted the frequency of the first resonance versus component spacing. So you can see here, for this case, the circuit simulation predicts practically no change in that first resonant frequency for this configuration as your spacing is varied. However, the 3D EM simulation is actually correctly predicting the trend of the shift in the resonant frequency as spacing is changed. Now, the same test that was performed with inductors is now performed with a 603 size capacitors, same test picture and everything, also in the shunt configuration. So a similar issue was present here in this circuit simulation, and you can see that although the circuit simulation results are a bit closer to the measured data in this case, the circuit simulation still fails to accurately predict the shifting resonances as component spacing is varied. Once again, compare this to the full 3D EM simulation results on the right-hand side, and you can see that the resonances are now being correctly predicted once we bring in all of the 3D coupling effects that are occurring in the structure. We also plotted the frequency of the first resonance versus component spacing for this case. And for the closest spacings, the circuit simulation is not able to predict the shift in the resonance as accurately as the 3D simulation. From previous work that we've done in this area, we know that much of the coupling between closely spaced capacitors can be attributed to pad-to-pad coupling. So far, for the capacitors, the circuit simulation or planar EM simulation results are closer to measured data than in the inductor case. However, for this test case, the actual components themselves are coupling, making 3D EM simulation necessary, particularly visible in the closest spacing case. So the next few slides here, I'm going to be covering examples of other models that are included in the Complete Plus 3D library. So on our first slide here, I have the results for a mini-circuit LTCC high-pass filter shown on 3 Rogers substrates. The cutoff frequency for this particular high-pass filter is 3800 megahertz, and the model versus measurement magnitude and phase are shown on the right for both S11 and S21. And you can see that the model versus measurement results are predicting are trending correctly. Similarly, here are results for 3 inductor values that are part of the Quillcraft A0XT inductor family we have modeled. Model versus measurement magnitude is shown on the right for both S11 and S21 on 3 FR4 substrates that we have measured. This next slide is an excerpt from the data sheet that we have for the capacitor using the coupling study shown previously. Here are results for the single capacitor value that we currently have modeled in the Johansson R14S family. Model versus measurement magnitude is shown on the right for both S11 and S21 on 3 Rogers substrates. And you can see here I'm also displaying the test picture that the model was both measured and simulated on for validations, as well as some example EM field views. This is an excerpt from the data sheet of the inductor that was used in the inductor coupling study. And here are the results for 3 of the inductor values within the Quillcraft 603CS model family. Model versus measurement magnitude is shown here on the right for both S11 and S21 on 3 Rogers substrates as measured. A little bit different of a validation is shown here. We have a 3D model for the Gigalane SMA connector, and for this particular validation, we placed two connectors in a back-to-back configuration on a through line using an R60 board mounted on a carrier. So the reference planes for both the measurement and the simulation are set outside the coaxial connector as indicated by the black dashed lines. This was set by a coaxial calibration. Model versus measurement magnitude and phase are both shown here for S11 and S21 of this configuration. And our final example here is a validation performed for the very 5mm QFN package model in our library. This package was mounted on our aluminum motherboard, and a through line was mounted within the package itself. Bond wires were then used to connect the package pins to the through line. The reference planes for the measurement and simulation are set outside the package at the package leads. Model versus measurement magnitude and is shown for S11 and S21 for this configuration. Now, one of the unique features and very popular features of all of our models is that they come fully documented with a model data sheet detailing model features, information on model development validation, input parameter descriptions, reference plane information, and plots showing model to measurement comparisons. Here's a brief demonstration of how the Modelithics library actually looks in HFSS. So to view a model data sheet, you simply place the component from the palette into your schematic, you open the Model Properties window, and then under the Component Properties tab, you click the Info button, and this will cause the model data sheet to pop up. So in conclusion, today we covered when equivalent circuit models can be useful, when 3D EM models are needed, and difficulties encountered when trying to create 3D EM models. Modelithics' extensive model library can be a great benefit to RF and microwave designers that are looking to perform these sorts of simulations. 3D EM analysis offers designers added insight into their circuit performance, such as coupling and component interactions, that are not achievable with other simulation methods. However, creating 3D EM models requires proprietary details that not all designers can access. Additionally, 3D EM simulation setup of these models is not trivial, and measurement validation is needed to ensure accuracy. By combining ANSYS's encryption technology and Modelithics' modeling expertise, ANSYS and Modelithics are working together to help designers overcome these challenges. Modelithics is using our trusted relationships with component manufacturers, our extensive measurement validation database, and our modeling expertise to continually add and develop content in our libraries. The Modelithics Complete Plus 3D library for HFSS contains a sample library of encrypted 3D models that designers can use in their simulations today. Thank you.